Okay, we talked a little bit about how electrons, or charges, any charged particles behave in electric fields. That is, whenever there's an electric field present, an electron will experience a force. A charge will experience a force. So we're going to kind of extend that and talk a little bit about magnetic fields and magnetic forces, which are slightly more complicated. Magnetic fields are caused by moving a charge. So if there's a charge moving, it will create a field. So if you've got a charge by itself, just flying along, it will have a field around it. If you've got many charges moving in a wire, there will be a field around it. There will be permanent magnets have metal, usually iron, but there are a number of other materials that are magnetic, that have the electrons in their actual material moving in certain ways that create a magnetic field. So slightly complex from a material science point of view, but the short version is that any moving charge creates a field. This is where we get to the physics gang signs. If you've got a field going in the direction of the fingers and you've got a charge moving in a field in the direction of the thumb, then it will experience a force in the direction of the palm. So that's one way to do it, it's just a flat hand. So I've got a field going upward, I've got a charge moving that way, then the force will be that way. I like this one because many fingers, many field lines, thumb, the direction you would hitch a ride, not that we do that these days, palm, the direction you would push with a force. So it's quite nice, but there is this one as well, which is much more gang signy. But you have to remember what each of the three fingers means. So it's the same thing though. Index finger is field, thumb is direction of motion, third finger, middle finger, socially not very polite finger, is the direction of the force acting on the moving charge. So whichever you use. So I've kind of slid over there, but when you actually have a field existing and a charge moving with respect to the field, it will experience a force. So you have a force that arises from a particular moving charge, and then you have another charge, and that charge will experience a force due to that field, but only if it's moving. If it's stationary, the force will be zero, and we've made that point in a minute. If the charge that you're talking about is positive, right-hand rule. If the charge you're talking about is negative, left-hand rule. I mean, again, people often go, well, if it's positive, it's going to push to the palm. If it's negative, it's going to push to the back of the hand of the right hand. But it's reasonably easy to remember right hand positive, left hand negative as well. When the particle's not moving, there's no force acting on it. So we've got some equations. For the force on a particle which is moving in a field of strength B. So magnetic flux density, the measure of magnetic field strength, is B in Teslas, is the unit. Tesla obviously now makes fast electric cars, but you might know the story of Nikola Tesla, who invented a variety of things around electricity and is immortalized in this unit. So if you've got a charge little q moving at velocity v in a field B, and an angle sine theta. Now, sine of 0 is 0, sine of 90 is 1. Right? If you imagine the sine curve, when you get to the 90 degrees point, or the pi on 2 radians point, it's equal to 1. It's at its peak. So if the angle is 90 degrees, in other words, if the particle's moving at right angles to the field, then it experiences the maximum force. If the particle's moving in the same direction as the field, right? Right-hand rule, but I've got my field lines and my particle's moving the same direction as the field, then it's sine theta equals 0, sine 0 equals 0, it'll experience no force. It's only the components that are moving at right angles to the field that will experience a force. Hopefully that's clear. So the force is B, V, Q, sine theta. So if theta is 0, that goes to 0. If V is 0, that also goes to 0. Right? So a charge that's just sitting there will experience no force, and a charge that's traveling in the same direction as the field will experience no force. And if it does experience a force, it will be this mutually orthogonal thing. It will be like that, all at right angles to each other, or like that. If you have a bunch of charges moving together as current in a wire, so we can have basically, you can see that that formula is very parallel. So you've got the F equals B and you've got the sine theta, but you've got I, the current, times L, the length of the conductor that's traveling in the field. So same deal. If the conductor is at right angles, 90 degrees to the field, maximum force. If the conductor is along the direction of the field, same direction as the field, zero force. And if the current is zero force, obviously. So knowing these, and again, obviously we'll do some examples and work with them a bit. So that's forces of, and that kind of makes sense that if a charge that moves relative to a field experiences a force, if I grab a wire, just a chunk of wire, a chunk of a metal rod, anything that conducts, and move it through a field at right angles to the field, then all the electrons in that conducting thing are going to experience a force. And they are going to move because they can move, right? It's a metal, metallic bonding, free electrons floating around. They're experiencing a force, so they'll move. And the electrons will move up to one end of the wire, so that'll be negatively charged. The other end of the wire will be positively charged, right? So there'll be a voltage difference, a potential difference between them. We talk about it as an EMF, which is a dance music band from the 80s, but also a unit of voltage, basically. It's the same kind of unit as a volt, but we talk about the electromotive force, the ability to do work, so the voltage, the potential. So an EMF, if I take a conductor of length L and move it at velocity V through a magnetic field of strength B, I'll get a particular EMF, right? It's related by this particular thing. So that immediately suggests to me, hey, I can build a generator. I can use that tool, probably not just a straight wire moving through a field, because that's a bit difficult, but you know, maybe some coils or other things. I can actually generate electricity if I want it from kinetic energy, turn kinetic energy into electrical energy, which is what a generator does. The magnetic flux, phi, in Webers, a Tesla is a magnetic flux density, which is the number of Webers per square meter. But Webers per square meter have the SI unit Teslas. A Tesla is a Weber per square meter. So the magnetic flux passing through a surface of area A, so it can be a square, circle, whatever, it has surface area A, which is at theta degrees to the field, of strength B, is given by phi equals BA cos theta. Now, we're using cos instead of sine. So what does cos do? When the angle is 0, it starts at 1, and when the angle is 90, it goes to 0. So when the surface area is okay, this is slightly confusing. Here's the surface area. Here's my surface. It's got area A. Now, when I want to talk about the direction of that, the best way to actually specify that direction is with a vector coming straight out of the middle of it at right angles to every surface on it. Right, so we call the direction of that surface this vector that's coming out. Right? Now, if the field is coming across this way, here's my field, it's this direction, and the vector in my area is in the same direction as the field, the angle equals 0, then my area has its maximum face to the field, to where the field's coming from. Does that make sense? That's going to be a lot easier when I draw a diagram as well. So when the angle is 0 between the vector coming out the middle of the area and the direction of the field lines, then you get maximum flux through it. When it rotates around 90 degrees, your area is facing that way. None of the field lines are getting through the area. You're not getting flux through the area. Does that make sense? When it's turned around that way so that they're at the same angle, you're getting all the flux, the maximum. And as that cos changes, right, you can imagine your area rotating and getting less and less field lines through it until it has 0. Hopefully that's clear, but as I say, it'll be clearer once I can draw some shaky diagrams. When we actually change the flux going through a loop, so That's just a flux through an area that I was talking about. But if we have a flux going through a loop of conductor so that the electrons can move, then when the flux changes, so either I've got my area and the magnetic field strength changes, or I've got my area and I rotate it, my loop of conductor, I rotate it, that will create an EMF. That will create a force on the electrons that will make them move in the circuit. So, and if I've got one loop, I'll get it one time. If I've got two loops, I'll get it twice. If I've got three loops, I'll get it three times. If I've got n loops, I'll get it n times. So this is, there is a name for this law, which I've momentarily mislaid overall. Lenz's law is one tiny piece of this law. Doesn't matter, I'll drop it in the discussion board or something. So the EMF in that particular loop, or set of loops of wire, or conductor, whatever it is minus n times the rate of change of flux, d phi on dt, or delta phi on delta t. D phi on dt would be the way that we would integrate, differentiate it if we were using calculus to deal with this. So delta phi, the rate of change of flux through the loop. But we also had said that the flux through the loop is BA cos theta on the previous slide. So, right, phi equals BA cos theta. So we can just substitute that into this equation, minus n BA cos, change in BA cos theta over delta t. And you can see that to change BA cos theta, you can change B, this field strength, A, the area. You don't tend to make your wire loop get bigger and smaller, but you could. That would achieve the same thing. Or cos theta, the angle, or theta you change. The negative sign is kind of interesting. It's Lenz's law, which means that the induced current will be in such a direction as to oppose the change causing it. Now, those of you who do know some chemistry will be familiar with Le Chatelier's principle, which is if you impose a change on a system at chemical equilibrium, the system will change so as to reduce the size or to oppose the induced change. So these laws actually happen in both physics and chemistry. There's Lenz's law in physics and Le Chatelier's principle in chemistry. It sounds like nature being difficult. It sounds like the universe going, well, you try and change something, I will oppose you. But just think for a second about what would happen if it was the other way around. If you imposed a change and the universe tried to help you impose the change more, and then you imposed some more, you would actually get this feedback loop that got bigger and bigger and bigger instead of smaller and smaller and smaller. The fact that these, there are these kind of self-limiting factors actually make life much safer. Here's an illustration. If you've ever seen the Robin Williams movie Flubber, where he coats a bowling ball in a material that allows it to bounce higher than it started from. So it will bounce 1 meter and then bounce 1.2 meters and then bounce 2 meters and keep getting higher and higher. That's what would happen if there wasn't this minus sign, if there wasn't Lenz's law and Le Chatelier's principle. Systems would get out of control and get bigger and bigger and bigger. In the movie, the bowling ball keeps bouncing higher and higher until it's bouncing into space. And it's incredibly dangerous because it's falling from great heights and so on, because there is not this kind of self-cancelling system. Okay, small philosophical note, but hopefully interesting, that the minus sign, the fact that the universe opposes the change that, and you know, this I'm making it sound now as though the universe has a will. Clearly it doesn't. The way that material and substance is opposes the change that we impose on it. So if I'm trying to rotate the coil this way, the EMF will be created in such a way that it tries to rotate the coil that way. Right? It will always oppose the change that you're trying to do. If I'm trying to make the loop smaller, the EMF will be induced in such a way that it tries to make the loop bigger, and so on. If I'm trying to reduce the magnetic field, an EMF will be reduced. That will create a new magnetic field that tries to make the field bigger, and vice versa. So hopefully interesting. And I've been talking about transformers along the way. I haven't been talking about transformers. I've been talking about generators. So a generator, you move a conductor through a magnetic field and create a current. An electric motor, you put a current into it and it causes a conductor to move in a magnetic field and creates a force. They're basically the same things. You can actually, depending on how it's designed, drive a generator in reverse as a motor and vice versa. They basically, one, you put put electrical energy in and get kinetic energy out. The other, you put kinetic energy in, so you drive the generator with a steam turbine or an internal combustion engine or usually a steam turbine, water from a hydroelectric system from up high in the mountains. There's a number of ways to turn your turbine, create kinetic energy, turn it into electrical energy in a generator, or use electrical energy, drive it in, put it into an electric motor and create kinetic energy. The two things are related. Transformers are kind of cool. This is one of the reasons why alternating current is better than direct current. There was a big fight between Edison and Tesla about alternating current and direct current. And it's fascinating to read up on. I won't talk about it here too much, but Tesla discovered alternating current and it ended up being the standard. And one of the reasons is transformers, because if you take one coil and couple it with another coil, so we have an iron core, then one coil is bigger than the other, then drive it with an alternating current, you're creating and collapsing magnetic fields because you're driving back this current, and that will induce magnetic fields in the other coil of the transformer. And you can step up or step down the voltage. So we need 240 volts in our house. But remember I said maybe 2 weeks ago that we want very small current, high voltage, small current in the overhead transmission lines. So we want 110,000 volts in our overhead transmission lines, but we don't want 110,000 volts in our house. So we use transformers to step it down again. And we initially used transformers to step it up from the generator to the transmission lines so that it's transmitted at these high voltages. So AC can be transformed to higher and lower voltages and correspondingly higher and lower currents using transformers, which is why AC is so great for household use. So again, hopefully interesting, relevant. So much of this stuff relates to what we do in our everyday lives. We use electric motors in heaps of things, from the car window openers and window washers to a very wide variety of things, of which none are immediately presenting themselves to my mind. And obviously we use semiconductors and other materials. So it's been a pretty quick run through electromagnetism. We didn't talk about, actually I'm going to make one more little video, I think, to talk a little bit about the induced electric fields, B equals mu naught Ni and those kind of things. There's a couple more formulae and a couple more concepts that I think I didn't include in this and that I would like to include. So you'll see that one after this one.